Okay, so as Favonia mentioned, there's a bunch of information. So yeah, this is where I have I think I mentioned this last time, where I will try to keep the schedule, and I will make links to the various notes that have been taken by the students as the semester goes along. So I'll just have your name there and then link to them, so that will be a good reference, and we'll put links to any exercises that we write out and so on will be available there. It's all a little kludged together, but basically nothing does everything that you want it to do in an easy way, as far as I know. So Piazza, I set up a Piazza webpage. The main reason for this is kind of to give us the ability to have a discussion group and to make announcements and keep things up in real time, so you can have a look at that. That's there. I and Favonia both actually put a couple of announcements out there yesterday, so you could have a look at that. In particular, it has a convenient little mechanism for finding partners for writing course notes and stuff. So Favonia started that one up, and we're trying to use that little machine, so that's kind of convenient. So you should definitely have a look at that. We'll be using that actively. And then for the note taking, this is what will happen if we divide by n here. We figured out that everybody will be responsible for 2 note takings per semester, and so and Favonia is going to organize all that for the schedule. We'll put your names in the schedule, and he set up a GitHub, which isn't mentioned here.
Oh, we're still doing experiments on it. I'm still experimenting on it.
Okay, we might set up a GitHub so that all of the sources and stuff for the notes will be in one common repository, and that will allow us to make edits and changes after the fact and stuff, so that we have a reasonable record of what we've done this semester, that we can polish up and stuff and make corrections and so on. So we're going to do that. And there we're kind of somewhat ambitiously following the model of the hot book, which I waved around yesterday, which is a completely open source thing. There's a GitHub for it. You can link to it. The link is on the homepage. And people, if you see a typo, you can make a correction yourself, and then you submit a pull request, and then one of the authors will review your request, and 9 times out of 10 it's a typo, and then it just gets pushed into the source. So we're going to try doing the same thing here. So it'll be hopefully we can have a nice collection of notes by the end of the semester. And I mentioned that my expectation is that I don't mean to be overly emphatic, but I guess I'll mention it a second time, which is my expectation is that you're going to take pride as an author when you're writing those notes, and that the idea is not to regurgitate whatever it is I said, but rather to take what I said and form it into a self-contained narrative that fills in details, corrects my mistakes, which I will probably make, and makes things more precise than I may have been able to make at the board. And if we do that, then that will be your contribution. It'll have your name on it, and it'll benefit everyone, because I can't always anticipate what a student perspective on a particular topic is, and what things I ought to have said and didn't say, because I try to do that, but I can't always succeed in doing that. So if we do this in a way that's more works back and forth between us, then hopefully we get a better outcome, and it's a better learning experience for you. And so I think that's the reason why I want to do this. So we'll see how that works out. Okay, so that's all the admin stuff. So right, maybe you don't know this. I don't know if you know this. The way we're doing it is you self-register for the Piazza. Okay, so I think we pre-registered everyone who was on the university.
Well, I'm only able to send the invitation to all the
invitation.
Android email.
Yeah, everyone who was on the official university database as having signed up for the course we sent you all an email, right? I'm pretty sure, because we made a list and did that. But that's like, I think, a fraction of you. That's not everyone. And I have no other way of knowing who you are. So, and it's stupid to pass around a piece of paper. So what you should do is go to this page and sign yourself up as a student, even if you're like a faculty member. But for the purposes of this of this exercise, you'll be a student, and so you can sign yourself up, and then that gets everyone gets everyone onto the available to us, so that I can reliably say, I can think, okay, if I put something on the piazza, I assume you've seen it. And that's basically the idea. Okay, so that's what we'll do, and I think that will work out. Like logistically, that should work out pretty well. Okay. All right. I'm going to erase all this stuff now, if you don't mind. Thank you, Favonia, for putting all that up there. All right, good. So where we were last time is I wanted to try to develop a kind of some, extremely basic things in order to illustrate some fundamental ideas that will permeate the course as we go along. So what we were doing is we were looking at first the negative fragment of intuitionistic propositional logic. And we had this notion, the way I got as far as the following two things. I didn't get too far, but I got as far as the following two things. Or three things, actually. So we were looking at sort of truth. That's always a nice thing to think about. So we had the notion of the trivially true proposition, which we called the true formation rule. And we organize things into introduction and elimination. So we have truth introduction, and truth introduction simply says the trivially true proposition is true. So already I'm illustrating the framework that we're using. I'm going to leave some room over here. So the framework of judgments that we're using is we have a judgment of A expresses a proposition. We have A expression is true, and then I'm going to say some other things which will go here. So we wrote down some rules like this, and I was illustrating the principle of conservation of proof, or Genson's inversion principle. And so because nothing went into the truth of true, then nothing can come back out of it. So that's the idea. So there's no elimination rule. So that would be truth. And then we did conjunction. It's nicely. So the three connectives I'm doing are particularly well behaved. So we said that A and B, or like that, is a proposition. So this is the formation. If A is a proposition and B is a proposition, so that's simply a rule of grammar, if you will. What sort of things constitute propositions? And then we looked at the introductory rule, which says that the truth of a conjunction, and then, okay, I will tip my hand a little bit here. I'm actually playing a little trick on you. For those of you who haven't seen this kind of thing before, I'm going to lead you down a garden path, and you're going to find yourself in a slightly unfamiliar territory shortly. So that's why I'm doing all this. But bear with me. So right now you can go half asleep and think, oh yeah, I know all this, and then I'll show you, but maybe you don't know everything, and so we'll see. Okay, so this is the idea. And introduction says if a conjunction is true, then if the two conjuncts are true, that's what else could you possibly imagine it to be? Oh, and there were two elimination rules, so the and elim, I don't know, I might have called it one or left or something like that, which looks like this. If A and B is true, then A is true. And so these are our rules of deduction. Now, I already mentioned last time, and I will emphasize this again a little bit later. At first, we're going to write these things down as a formal system and sort of be precise about what we're doing. But then the idea is to sort of, get used to that and then just starting writing things out in a more informal math style. But I want to know, like, what are the actual rules of the game? And the reason is because of mechanization purposes, that we want to have the rules down precisely because that's what the computer is going to understand. It doesn't do very well with, oh, you know, okay, it's not so good with that. So we want to make sure that we know what the rules are, so we set them down. And also, for reasons that will become apparent by the end of this lecture, the rules are going to give rise to some structure, this idea of proof relevance, that is going to matter a lot. So that's the reason why I'm doing this. So don't worry, we're not going to be spending our whole semester just writing down rules and stuff. I'll show you where this all is going. Okay, so those I would consider to be the defining rules for conjunction. You might ask, like, what makes these rules good? And I'm going to say something about this, like what makes this the right set of rules. Like, so far it's sort of hard to think how I could make a mistake, but anyway, just to like give you a kind of flavor, I mean, of a deliberate and horrible, egregious error. If I left out that premise for this rule, but I left these two elimination rules in place, you can see that there would be some kind of coherence lacking between the introduction and elimination. That notion will be made precise shortly, because let's say I had accidentally omitted this premise, then over here I would be getting something from nothing, okay? And so something must be wrong. And the something has to do with what I'm going to do over here, but there will be some coherence criterion. And the other way around is, if I left that rule alone and I wrote this rule down but forgot this rule, let us say, and left that out, then there wouldn't be anything, so to say, positively wrong in the same way that this other scenario was wrong, but there's still something a little broken because I failed to take full advantage of the information that went into what the introduction rule that determines the conjunction. And I didn't extract, let's say if this were not there, then I was failing to extract information that I put in. So you can imagine that something else must go wrong, okay, in that scenario. So the beauty of the Genson's insights is that there's a very nice bunch of tools that we'll mention and discuss here that allow us to assess the internal coherence of these rules, and it's what really gives rise to the computational interpretation of the theory. So I'm just giving you a little hints of like where these things are going, because I guess I want to say, and this is something I'm eventually going to criticize the homotopy type theory on, is that the rules are not arbitrary, and you're not sort of, the whole game of what we're doing here is not to treat type theory as just yet another axiomatic theory that happens to be my favorite one. Okay, there's something whereby, like first order logic would be your typical axiomatic theory. It's not like that. And the reason is that I expect things to fit together and to have certain computational properties, which I'm going to explain in a minute. And lacking that, I think it isn't a fully satisfactory type theory. So there's something very specific about the way type theory works that's not like, oh, somebody's version of, some version of higher order logic or second order logic, anyway, where you just write down a bunch of things and you justify them by maybe a model construction, which, as we know, is just comparative linguistics, but you somehow decide that this other language is more meaningful than the one you're studying, and then you compare them and you justify it in that way. That's not sort of the way we're going to do things. So anyway, just maybe not everything can be appreciated right now, but I just want to give you a flavor. These things are not just arbitrary set of axioms. There's some internal coherence that matters. So where we got to at the very end last time was the rule for implication. So we said we can form an implication by forming take two propositions, then I can form another one, which is the implication of those two propositions, and then we define the truth conditions for those implications. So this is where we got at the very end, just to remind you. So this is where we are. So implication introduction says, how do I know that an implication is true? And the way you do it is, the basic way to do it, let us say, is we deduce B from A. So this is an example, by the way, the terminology, I guess, I'm not entirely sure who my audience is here because I don't know all of you. So you may or may not already know that this formulation is what Gensen called natural deduction. I don't know, you might have heard that before. Okay, so that's the formulation that is being used here. And it's called natural deduction because, well, it feels pretty natural. If I ask you to prove an implication, the typical thing you're going to do is show that A entails B. As opposed to unnatural deduction, which would, nobody ever called it that, I just did. Unnatural deduction, which is the classic kind of Hilbert system, which you will find in almost any textbook on logic. And the way those things work is they write down a bunch of, until you know the inner game, they look utterly arbitrary. They write down a collection of like 5 or 6 axioms, okay, about implication. There are these complicated implications, and you think, whatever the hell that is. Okay, they write down a whole bunch of implications, and then they give you one rule, which is the rule of implication elimination, which is, we mentioned last time, that says, if I happen to know an implication is true, and I know its antecedent, then I know its consequence. So this is in the classical literature, this is pretty much invariably called modus ponens because who knows, I don't know, somewhere along the way someone classified these things and used the Latin words for them. Okay, they must have been British. Okay, so they wrote these things down. So typically you don't get this, if you're not familiar, you don't get this looking rule. This is the innovation of Gensen. Okay, that's important. Funnily enough, though, as natural as it is and as beautiful as it is, in my opinion, all the textbooks don't, they rarely do. If they discuss natural deduction, it's in chapter 41, and they say, oh, you know, there's this other thing. Okay, and I think it's kind of like unsatisfactory. But anyway, that's the way it is. Okay, so those were the rules. So in order to explain this rule, at the end, I was explaining the idea of entailment. So this is called entailment, or logical consequence, it can be called, and maybe there are other words for this as well. Okay, but that's what that is called, which is a what I might call a higher order judgment form. So these are sort of, in this setup, are basic judgments, or basic or atomic judgments. Okay, and then we have some compound ones, which at this level of simplicity, I don't need anything else than this, which is the following idea, in fact, which is a very basic concept, which is a logical entailment, and this invariably is written gamma, okay, which is, and n is bigger than or equal to 0. All right, so you can have that, any number that you have here. And it's supposed to express the idea that A follows from A1 through AN. And there are many ways to think about this, but as I say, you can think of these as being assumptions from which you're deducing a conclusion. So that's what's being, here's a onery case. N is equal to 1, and I assume A is true, and I deduce B from it. Okay, so I'm going to now, there's something important now that has to be explained about what this notion of entailment is. So I am going to explain that in a second. But before I do that, I want to say something about the nature of these rules. Okay, which is a little, which we should be careful about. So I'm not entirely sure where's the right moment for me to bring it up. Let me defer it. I'm going to say something about these rules having to do with uniformity, which I'll come back to in a minute. But right now, let me just talk about the notion of logical consequence. So the idea is that what are the properties of logical consequence? Let me just write entailment. It's a little shorter to write entailment. Okay, this is what I want to do here. And it's also called, so this is called, as I mentioned, entailment. Or it's also called, especially by Martin Leff, it's also called the hypothetical judgment. Because it's a judgment made under hypotheses. Okay, so those are the hypotheses. So, but I've already foreshadowed a few things, so I will feel free to continue to foreshadow things. So the intuition is, from the point of view of logic, what's going on here is I'm going to be defining for you what is the concept of a mapping. Okay, that is what is going on here. And the fact that that's going to constitute a mapping will emerge in this lecture. But we can think of this as a mapping. It's a mapping from these sort of inputs, if you will, to that output. And as I was mentioning last time, and what is very clear when formulated in natural deduction, is that the concept of a mapping is prior to the concept of the collection of mappings as an object in your category. There's a category lurking here. And it may or may not be. Here it is the case that the prior notion of mapping can be internalized as an object in the category, which is going to be called an exponential. And I'll say more about that in a second. Okay, but it's important to discuss the idea of a mapping. So for those of you who know where I'm going, you can see where, well, you know where I'm going. Okay, but so let's write down now what are some properties of entailment, okay, that make it an entailment relation, and then I'm going to reformulate them in a way that may look more familiar and standard for you. So there are many ways to write these things down, but I'll write down a few basic ones. So one is the principle of reflexivity. If I'm going to express a concept of this follows from that, most assuredly, I must say, whatever you assume follows from that assumption. That's like the most basic thing. And this is some kind of principle of reflexivity, which I will write over here. Okay? So it's some idea. You can think of this as reflexivity. And I'll show you in a minute another way of notating things that will make some of those ideas more blatantly obvious. Okay. Second thing, which is like absolutely essential to being a notion of entailment, is the idea of transitivity or composition, which will say, if I know that A is true, and I assume it's true for the purposes of showing that B is true, then I can simplify that whole scenario and know that just B is true from gamma alone. And this could be called transitivity, and I'll write it like that. And in fact, I think in my notes I wrote it like this, where for various reasons I want to write it like that. So let me just do it. Okay, so I'll do it like that. Okay, in the end, various formulations are all going to end up being the same, but I think I wrote it like that in my notes. So let me stick with that. Okay, so this is the lemma rule. If you prove a lemma and you prove a theorem following from the lemma, if you really wanted to, you could include the whole damn lemma, okay, inside your own proof and get a proof that doesn't depend on the lemma. So this is inlining, right, from a computer science point of view. I can just inline the code for this and never mention the lemma. I could just reprove it in place every time. Everybody knows this is obvious, okay? And I'm just saying that the notion of entailment certainly had better satisfy these two properties. Otherwise, it doesn't really qualify as an idea of an entailment. Now, there are three other properties which I think of these, like I can put stars here. I think of these as like indefeasible. These are principles you can't possibly deny. There are a few others which you could deny. Okay, but for our purposes, we are going to stick with them. And they are the following, which the most simple one is that, well, maybe not, I don't know. A simple one is, if I prove A from a bunch of assumptions, I can, for the hell of it, think of it as vacuously proved from an additional assumption that's got nothing to do with anything. Okay, all right. So that's the idea, and this is called weakening, because this statement is weaker than that statement, right? If I entail from something, from an additional assumption that actually I don't need, then I've said something less than I could have said. Okay, so that's the principle of weakening. The principle of weakening is important in a number of ways, and that if you're not familiar with formal logic at all, you'd be surprised how often weakening comes up. But it's a principle that we have. I want to mention, just as a nod to people who may know about such things, you could consider denying this principle. And if you deny this principle, that's one aspect, but not the only aspect, but one aspect of what is called relevant entailment. Whereas the idea of relevant entailment is that when you write down an entailment, you are not only saying that this follows from this, but you're saying it relies on everything that we see in here. It's not allowed to have irrelevancies, okay? So that leads to a subject called relevance logic, and that's of no concern to me in this semester. But I just kind of want to mention one could deny that. And there's a similar one that you could deny that in some way seems self-evident, but one could deny, which is this, which is if I use a lemma twice in proving a theorem, there's no point in stating the lemma more than once, because I can appeal to it twice. And that's called contraction. You're contracting those into one. This again seems utterly the whole point was I didn't want to put stars there, or I could have done it the other way around. Anyway, I wanted to indicate which ones you couldn't possibly do away with from the ones that you could possibly do. Okay, and what was I saying here? Oh, yeah, so if I'm allowed to appeal to the lemma twice in my proof, then, there's no point in writing it down as two separate lemmas and appealing to that. However, this is also something that in certain situations, like related to relevance logic, one might argue I don't want to have that because I want to keep a proper accounting of how many times I used a lemma. And one can do that, and I don't want to discuss that either at the moment. And then the last one is very awkward to write down notationally. It's called exchange, which says that the order doesn't matter. So let me cheat a little bit because it's such a pain to write down. Let's just write pi dot gamma here as a true, where what I mean is pi is any permutation. So I can permute the order of the assumptions. So the idea here is, like in a textbook, you always refer to lemmas by, paren 3.2 or something like that. So you don't really care what order those lemmas came in. I mean, it has psychological significance, but mathematically, number them whatever way the hell you want. Okay, all that matters is that underlying it is some DAG, and so the order of the lemmas that you state, apart from psychological considerations, completely doesn't matter. Okay, and so that's what the permutation rule is doing. And this is another one that is deniable. These rules are deniable. People have studied forms of entailment in which these aren't true. Okay, but in my case they're going to turn out to be, I'm not going to go there, that just happens to be another topic. Okay, but these two things, I mean, you're never going to get away from those. Otherwise you're not really talking about entailment, I would say. Okay, so these are what are called the structural properties. In fact, when you include all of them, then we say it's a structural entailment relation. And if we deny any one of these, then it's called substructural, just so you know. That certain of the structural principles being left out makes you substructural. Okay, but we're going to be looking at structural entailment. So these are called the structural properties, and they look like that. Okay, so now that allows me to, with that sort of machinery in place, allows me to make a little move here that is probably familiar to many of you, but I'll do that. So we write down these rules. Oh, okay, yeah, I do want to say one other thing, okay, at this point. I'm not sure what is the best moment to write. I keep hesitating about what is the best moment to write it down. Which is a different way of form of, let me just make a remark about the form of presentation of these rules. When I write the rules down in this form, what I'm doing is I'm writing them in what is called a local form, which is only the things that matter to the particular rule are written down here. But as a matter of fact, everything I'm going to be considering whenever I'm writing down, for example, this rule, mode opponents, I'm expecting it to be used in the presence of assumptions. So a lot of times people will write down, like they'll carry along a gamma here and write the rules like that. And the whole idea is simply to remind you, okay, that the rule applies even when there are assumptions hanging around. And one way to say it is, when I write the rule, that's like the local form, and the global form consists of sprinkling the gammas around everywhere. Or another way to say it is, it applies in any context, which is another way of saying this. So you'll often see people will write those down, but it starts to get heavy, so that's why I didn't write it down at the moment. So it's sort of implied, okay, that you do this. And by the way, you might ask yourself, why don't I write it like this so that I can write gamma 1, gamma 2, and gamma 1 and gamma 2? You could write it like that, but in the presence of weakening, then I can always weaken this to gamma 1, gamma 2, and weaken this to gamma 1, gamma 2, and thereby get gamma 1, gamma 2 down here with copies. And then using contraction and permutation, I can turn that into we'll just call that guy gamma, and then by contraction I can use gamma here. Okay, so that's why. Okay, so when people are concerned about the substructure of these properties here, then the rules are all very finicky, and you must actually write down where the gamma i's are because it matters when you don't have weakening contraction. But when you do have weakening contraction around, you can be quite cavalier. So we'll be pretty cavalier about these things. And so in the end, I don't really write it down, but I just want to mention to you, like, that's what's implicit here. Okay, everything can be done from the point of view of the assumptions. That leads to a point, though, which is it will turn out for our purposes to be interesting to consider the structure of closed proofs, proofs that do not involve assumptions, because they tell us something about sort of the observable outputs, or we're going to say, once I establish the computational content of this, they will tell us something about complete programs that you can run. And we want to know something about their behavior. So there will be times when I'm emphatic about insisting that gamma be empty. Okay, that will happen. There are certain scenarios like that. So we'll come back to that a little later. Okay, so I can erase this now. So now, well, it's inconvenient. I mean, you're going to have it committed to memory because I have to write somewhere. Okay, so I want to do something else, which is to relate all of this. This is a kind of proof theoretic style of presenting things, the Gensen style, using system of natural deduction. But there's another way that people say the same thing, okay, in a different way that is maybe more familiar to you, which is what I'm going to lead up to, which is the order theoretic formulation. And one way I can do this is to say this. Let us define an order on propositions. So A and B are propositions, where A, B, I'll write, are props, by saying this means that A true entails B true. And now I want to say something about this order, and I'm going to develop a little bit more machinery, in particular the negative fragment, in order to fully explain what I have here, which will then let me say something important about the structure of this. So let's define this as an entailment relation that we have here. In a few minutes, there's going to be a little bit of a noise having to do with the distinction between a pre-order and a partial order. So right now, I'm going to emphasize the following facts. So the first thing is that this is a pre-order. Okay? When defined this way. That is, it is reflexive, because that's the first structural property I mentioned over there. And it's transitive, because I can specialize the structural rule of transitivity that is written over there to show, what does that mean? That means that if A true entails B true, and if B true entails C true, excuse me, then I can put those two things together and know that C is true. Okay? So in other words, if A is less than or equal to B, B is less than or equal to C, then A is less than or equal to C. So we have the structure of a pre-order. Okay? That's the first fact. The second fact is we have meets given by conjunction. So the conjunction, the notation for the conjunction is we have meets or greatest lower bounds. So what does that mean? Well, let me write it out order theoretically so that it looks nice for you. So if I write this out order theoretically, that means A is less than or equal to A, and this means A is less than or equal to B, and B is less than or equal to C, then A is less than or equal to C. So it'll look more familiar to you. So meets given by conjunction. So A and B is less than or equal to A. And A and B is less than or equal to B. So in other words, this guy is a lower bound for A and B. Okay, it's below A and it's below B. And it has the property that it's the greatest lower bound, that if you give me any other lower bound of A and B, then it's less than or equal to the meet, which is the conjunction. So this is just what a meet is. This is the definition of a meet. Okay? Meets are given by conjunction. And it's nice to draw this as a picture using Hasse diagrams. And Hasse diagrams, in Hasse diagrams, it looks like this. You can write it, I often end up writing it like this. So you point, in this case I'm pointing to the larger thing. The diagram, the arrows point from the smaller thing to the larger thing. So the idea is A and B is less than A, and A and B is less than B. That's the first two things. And you say if C is less than A, and if C is less than B, then, and then a lot of times people will draw in a dashed line there, C is less than or equal to A and B. Okay? So the idea is that if this is the case, then this is the case. Okay? So that we have there. And many of you will recognize that what I'm getting at here is being a meet means meet equals product in the categorical sense for a pre-order. Because what is happening here is you can think of this as defining a degenerate kind of category where there's only, when I write A is less than or equal to A, I mean there's a unique map from A to A that I just mark with a check mark or something to indicate that it's an axiom. And there's only one. Things can be related in at most one way. And then you can just say if there's a map from A to B and there can only be one, and a map from B to C there can only be one, then its composition, which can be the only one there is, from A to C. So it's the restriction of a category to a pre-order. And if you think of it like that, then this is a product diagram. Okay, so the meet is a product. But there's no commutativity, or there is a commutativity, but it's trivial that these commute, okay, because there's only ever one arrow from any two endpoints because it's a pre-order, that's the starting point, and so that can't help but commute. Okay, and so you could write it like that. Later, shortly, we'll end up getting the additional structure there, and then these conditions will be significant. Okay, and the other thing is I could say we have a greatest element. or as it's sometimes called, the final element. Okay, and why is that? Well, it just simply says A is always less than or equal to truth. Okay? And the reason is true is trivially true, and so you can assume A in order to deduce it if you want, but anyway, true is still gonna be true. So whatever A is less than or equal to truth. So we're going to have a greatest element. Okay, so that's the structure. So right now we have a lower semilattice. Okay, so some of you might have seen this before. I think when you have meets, it's called the lower semilattice. Yeah. So what we have is the structure of a lower semilattice. We have a preorder with meets. Okay, now comes a little technical unpleasantness. Maybe I'm lying according to your definition of a semilattice. Sometimes people insist that semilattices be not preorders but partial orders. Okay, and partial order, just to remind you, so let's get this over with because it's one of those things. Okay, so what do you mean by partial order? Partial order means you have anti-symmetry, which means that if A is less than or equal to B and B is less than or equal to A, then A equals B. Oh, that's so depressing. Okay, this is like, I don't like such a thing, you can tell already. Okay, but very often people will, when they get around to defining that, they'll just, like the starting point is not a preorder but a partial order. Okay, you can do this. Okay, as I've defined things so far in the board, I don't have a partial order, and then you could say, no, you don't have a meet semilattice. And probably you'd be right, because if you pull the book down from the shelf, that's probably not what the definition is. Probably the definition demands anti-symmetry. But the problem is, what do you mean by equality of propositions, if you're thinking of this from the point of view of logic? Okay, well, I'm going to anticipate the whole principle of univalence, which I'm going to talk about later. The principle of univalence says, what could you possibly mean by equality of propositions that would be interesting? Okay, and the answer is that what you do is you simply define equality of propositions to be interprovability. Okay, so that this condition becomes trivial because this is defined to be the induced equivalence relation. This holds if and only if each is less than the other. In other words, A entails B and B entails A. So, for example, A and A is equivalent in this sense to A. It's not equal to it. At least if you have some prior notion of equality, then it's not obviously equal to it, but it's certainly equivalent to it. So you can get around all of the, like, you can get so then what you do, you can see what's going to happen. So what you do is, if you want to make my story really work, and if you're going to insist on a partial order, an anti-symmetry, then instead you can't do this, okay? What you have to do is you have to define this in terms of equivalence classes of propositions, which I'll write like that. And you have to show that this concept is well defined, but it is well defined because whatever representative I choose here, they're interprovable all the way. So you're on this side and interprovable all the way on this side, so it will not matter which representative I choose. And then you can go through and check that everything is the case. And then what this is saying is that the product, if you will, or the meet if we want to write it in that notation, the product of two equivalence classes, it's a theorem, is given by the equivalence class of the conjunction. And you can check this, okay? So you can check. And you will need associativity stuff going around, and you're going to have to of conjunction, and you'll have to prove all of that in order to make it work. So I'm not going to go through all the details. It's a little bit standard and not that interesting. But I just want to point out that there's a way in which I'm being a bit cavalier with the definitions, because very often people will demand that you have a partial order. But anyway, it gave me an excuse to talk about univalence. So univalence will tell us will imply that A is actually equal to B here as propositions. Univalence is going to say interprovable propositions are going to be regarded as equal. Yes?
The hot is using this symbol.
Yeah, I know. There's a notational problem, I know. The reason I know that, this is very common to use as the notation for the conjunction like I did here. However, unfortunately, when I start talking about hot, we end up using this term, this notation for something else, okay, and a different notation for what I've written here, okay, which is, if I wrote it like that, I would be better. So in the terminology, in the notation we're going to develop in hot, it's written like that. So A and B are equivalent propositions. I only did that because a lot of times people will have seen the written as a triple bar. But anyway, okay. So univalence will tell us that equivalence, which in the case of what will eventually be called mere propositions, there's a reason why it's called mere, and it's supposed to be a little pejorative. So mere propositions, what it means for them to be equal is that they are equivalent. That's one of the big ideas of univalence. The implication of this is the following. You can screw around with any equivalence relation you want at any time for anything you want, and have fun, enjoy yourself, do whatever you like. But it's a royal pain to be always worrying about well-definedness things, and in particular to always having to be manually showing that, for example, everything in sight respects the equivalence that you're working with. For example, you define mappings on some kind of space, and you have a notion of an equivalence relation, then you have to show that things are well-defined. That is, the mapping takes equivalent things to equivalent things. But if I decree that equivalent things are equal, the properties of equality take care of everything for us, because of course I can replace equals by equals. Of course functions take equal arguments to equal results. Equality has loads of properties, okay? And so the idea of univalence is equivalent, in this particular degenerate case, equivalence can be regarded as a criterion for equality. And then you can take full advantage of all the properties of equality that you could ever possibly want, and you don't have to think twice. So univalence is a principle of mathematical efficiency. It's mathematically efficient to, in many situations, to be able to do this, to say, oh, mere propositions, we'll call them equal if they're interprovable, or we'll say, we don't distinguish between equivalent propositions, we just consider them to be equal. And in informal math, that's like paragraph 1 or a footnote or something. And then you're supposed to apply that everywhere, and you're supposed to believe the author that everything actually works if you were to really do it in full. The idea about univalence from the point of view of type theory is it's a proper principle baked into the type theory, and in particular, the computer understands what you mean by this. It's not like, oh, everywhere I said equals, you really should paraphrase that as equivalent, and you really should check X, Y, and Z, and you just say, okay, I believe you. And maybe you spot check, but basically you believe the person. Here, computers that's not something computers can do. So there's a nice mathematical convenience to being able to deem that equivalent propositions are equal. So that's my first statement about univalence. So univalence is a mathematically efficient way of formulating arguments and conventions that are normally applied with some kind of meta remark of we do not distinguish between isomorphic spaces or something. Well, that will end up being a formal principle of type theory. So that's kind of a nice thing. So this is the beginnings of the idea of univalence. Okay, enough of that. So now I want to say something a little bit more. Are you guys with me so far? You should interrupt me. Are there any questions? Am I boring you to tears? Is it really, am I starting too basic? You can just quietly nod and no one else will notice. One person. Okay. I do think it's important that I go through all the basics because at least in my mind, these things are, you have to know everything like this in order to appreciate what's going to come up. So, and I get to choose because this is my class. So this is what we're going to do. All right. So, all right. All right. So let's go here. All right. So now the next thing I want to do. So that was what I called the negative fragment of intuitionistic propositional logic. And I bet you know what I'm going to do next. I call that the negative fragment. Now we'd like to do the positive fragment. And then that will give me a structure that is familiar and useful. So let's look at the positive fragment. I didn't write negative fragment down earlier, but of IPL. Intuitionistic propositional logic. You may wonder why I keep calling it intuitionistic propositional logic. That's because I'm sneaking up on you. Okay, so we'll see. So the first thing was the trivially false proposition. So we have falsehood as a proposition. So that's my falsehood formation. And falsehood being trivially false should certainly not have an introduction rule. There should be no way to prove false by a rule of the system. But it does admit an elimination form, and you have to see why, and it'll help once I do the thing on the next board to see why this is the case. And the elimination, the falsehood elimination, is the famous, ex falso quod libet, right? It says that from gamma, I can write it like this. It says if false happens to be true, then A happens to be true for A being any proposition. Now you might wonder, how does this comport with my principle of conservation or Genson's inversion principle? Well, it comports with it perfectly. Since there is no introduction rule, then this can't ever happen, and so I can write anything I want here. That's the idea. Okay? And so they do fit together. They do have this coherence principle. But there's an easier way to see why. So I didn't want to call those 1, 2, 3. I wanted to call the whole thing 1. Okay, and now 2 is going to be the disjunction. And that's where the action begins. Okay, because this introduces something important. So that's disjunction formation. Okay, which says you can disjoin any two propositions. That's the notation. And now the question is, what are the introduction and elimination rules for disjunction? So we're going to have an or introduction left or 1, whatever you'd like to call it, 2. And the idea is that if A is true, then A or B is true. A or represents a weakening, right? If the sun is out, it's either sunny or raining. You might wonder why the hell I would say that, but never mind. It's logical. Logic is not really doesn't really have a say about, doesn't force you to be interesting. Okay, it just tells you what it is to be sensible. Okay, so we can write, yes, did I make a mistake?
You should the intro instead of the limbo.
This is called the intro, yeah, not a limb. Yeah, okay, yep. Okay, good, yeah, those are the introduction, excuse me. Okay, and if B is true, then A or B is true for the same reason. And now the question is, how do we get the elimination rule? And we get that by Genson's inversion principle. So what we say is, if I know that A or B is true, all right, then what can I do with that fact? Okay, well, the idea is that how did A or B get to be true? Well, it got to be true by either A being true or by B being true, because that's what the introduction rules were. So what I'm going to do is I'm going to reason by cases on which one it is. So we say if C follows from A, and if C follows from B, then C holds outright. can be written like that. And that's called the OR elimination rule. And so the intuition, as I've mentioned, is I'm extracting the information out that I put into it. The information that went into this was one or the other of these. I can cover my bases in either case, so therefore C has to be true regardless. That's what is happening here. And if you think about it, for example, if I omitted that premise, then something would be broken, because you see, if I happen to prove the disjunction this way, the poor guy would not be taking account of that possibility, and God knows what you could get out of this, okay? A might be the thing in question, and maybe B doesn't entail A, and it wouldn't make any sense. So you can kind of see there, this will all be made a little more precise shortly, but you can kind of see that these things must fit together in some way. And so it's that fitting together that we have here. So that's the notion of disjunction. In terms of order theoretic properties, you know what I'm going to say here. What we have is a least element, or an initial element, as it's sometimes called, which is that false is less than or equal to A, modulo the little bit of noise about whether we are doing equivalence classes of propositions. Let's not worry about that. So we'll just treat it as a preorder. Okay, so we'll say false is less than or equal to A. Okay? That's clear. False implies anything. Okay? And the other thing we're going to get is we're going to get joins, or least upper bounds. Okay, what does that mean? A is less than or equal to A or B. B is less than or equal to A or B. Oh, there's something I forgot to mention previously. Oh, well, I'll do it now. Yeah, oh, sorry. Get rid of that. So that's first fact. And then the second fact is this is the least amongst the upper bounds. So if you give me another upper bound for A and B, then I will give it, this is the least amongst the upper bounds. So this is less than or equal to C. If I were working modulo these equivalence classes, it would be unique. Okay, because you can check for yourself. If I had two, like a join prime here, you'd be able to show that the join and the join prime are interprovable and therefore equal. That's what would happen in the partial order case. Okay, so it's unique, or you can say it's unique up to logical equivalence. That's just depending on how you like to talk about it. And in terms of the pictures, it's nice to draw the picture. So it says this: if I have A is less than or equal to A or B, and B is less than or equal to A or B, right? The fact is A is less than or equal to A or B, B is less than or equal to A or B, right? Now, if A is less than or equal to C, and B is less than or equal to C, that's what's being said here, then A or B is less than or equal to C. And if you were working with equivalence classes, what you would say is the sum, or the least upper bound of two equivalence classes, is given by the equivalence class of the disjunction. That's what you would say in the partial order kind of setting. Okay, but anyway, I just want to do this kind of diagram. And as I mentioned before, we're working with a preorder, so that commutes, and this commutes because it has to. And that will end up being more important shortly. And we get that following diagram, and this is called a coproduct diagram. And sometimes people call that a sum. So this is called the coproduct diagram, and the one I erased is called a product diagram. And then I forgot to say something about the order theoretic interpretation of the implication. I forgot about that. Okay, so I should have written that down. I should have written that down earlier, and then I forgot what I was doing. Okay, so let me check for myself that I didn't forget anything else. Okay, yes. All right. So now we have the idea of the exponential. So the idea is we have a notion of an exponential. And the exponential is written like this. So a lot of times it's written b to the a. Or I'm going to say that a implies b, or b to the a are exponentials. Okay? And what do I mean by that? Well, what I mean is, if we have, let me just check my notation. Yeah, if I have A and A implies B, if that is less than or equal to, well that, oh, excuse me, we'll get to that in a minute. This is less than or equal to B. So that's just modus ponens, right? If you have A and A implies B, or B to, this could also be written B to the A, then that gives you B. And then we say it's the greatest such thing. So the idea is if we have A and C is less than or equal to B, which is another thing that seems to behave like an exponential, because when conjoined with A it gives me B. What I want to say is this is less than or equal to A implies B, or B to the A, however you like to write it. That's the universal condition. And this is the notion of an exponential object. So as I mentioned before, okay, it ain't necessarily so. So if you look at it from a point of view of a, order theoretic structure, setting this aside for a moment, what I now have is a lattice, okay? So the structure I have is a lattice. In computer science, there's a very, very unfortunate thing that people like to throw around the word lattice as being synonymous with whatever it is they feel like, which could be pre-order or partial order. And I would rather we not do that, okay? So like in security context, they're always talking about the security lattice. I think they don't never know what they're talking about, or they're abusing terminology. So a lattice is a pre-order or partial order. They're like, that's that thing I mentioned, which has all finite meets and joins, okay? That's just what it is. That's a good definition. That's been around a long time. Okay, so that's established. So you don't get to sort of use lattice to mean whatever you feel like, because it has a meaning. Okay, so this is, we have so far the structure of a lattice. And then we have, in addition, we have the notion of an exponential. Okay, which gives us the structure altogether, modulo the business about partial order versus pre-order, the structure of what is called the Heyting algebra. Which is a lattice with exponentials. Okay, so we have an exponential like we have here, and that gives us a lattice, so a Heyting algebra. Now, the thing I want to say about a Heyting algebra, and some of you are asking yourself, there's something he didn't say. Okay, and I will leave this as an exercise, and I'll give you a hint about how to do this exercise. Defined this way, every Heyting algebra is distributive. Distributive means that if I have A and B or C, then that is equivalent, well, I'll use that terminal notation, to A and B or A and C. This is trickier to prove than you think, okay? And it's a very good exercise. So I will give you two hints. Okay, A, use the fact that you have exponentials. It must be, because if you don't have exponentials, there are lattices that aren't distributive. So you're getting, something is happening, so exponentials is part of it, okay? So use exponential. And then the other thing was, it's, in order theoretic terms, it's the most trivial thing in the world, but you can't imagine how useful this is, which is use Uneda's lemma. If you don't use the Uneda's lemma, I'm fairly sure you're going to, which I'll state here, you're going to get stuck, okay? Don't ask me why this works so beautifully all the time, but it always works. Whenever you're stuck, do this. The idea is that, in general, I'll just write it with little cases. You can prove that A is less than or equal to B if and only if, for every x, if x is less than or equal to A, then x is less than or equal to B. You can't imagine how useful this is. Okay, first of all, let's check that it's true. Suppose we have the right-hand side. Then I can take x to be A and use reflexivity, and I get A is less than or equal to B. Right? So by considering the identity, I can show you that A is less than or equal to B. So that's right to left. Left to right is completely trivial because of transitivity. If x is less than or equal to a, and a is less than or equal to b, then x is less than or equal to b by, I think that was 2 uses of transitivity. Okay? So that's it. There's nothing. Why would you even call that Uneda's lemma? Okay? Well, because there's a general, this is a very degenerate instance of a more general fact. But that more general fact is equally useful for all the same reasons. So here's a way of thinking about it. The way to think about it is you're trying to show that this entails that. So I don't know if this will make sense to you or not, but let's try. What we do is we look at what are called all the generalized elements of A. That is what's going on here. You say, pick an arbitrary other thing that I'm deducing from. Look at all the ways I can deduce A from a generic thing. Then I can deduce B from that same generic thing. So this is the idea of what are called variable elements, which Laveer emphasized in his discussion of category theory, which is one way you could say that category theory, at least in terms of a mindset, is very distinct from set theory, because in set theory you're encouraged to think of global elements, because you'll notice it's not going to be the case if I insisted this to be truth or one, this, you're not going to get the leverage, okay, out of this. This is not going to help you in many situations. Using something like that is not even true in general. So, but you could just say it's true. Is it if it's bigger than this, then it's bigger than that. It's not going to help you. This works with global. This is what are called global elements. These are local elements or variable elements, and so this is a very useful idea. Okay, so if you use this and you use exponentials, you'll be able to prove distributivity. Sometimes in the literature, how am I doing on time, by the way? Okay. Sometimes in the literature, people will define a Heyting algebra to be a distributive lattice. Somewhere they got to get exponentials in there. Okay, well, I don't know. Anyway, it's important that it be distributive. I've forgotten what I was going to say there. But you'll see it comes up. So it's important to check that it's distributive. Okay, and this is my hint about how you could do that. If the hints, you can just apply them formally, but if the business about points and stuff didn't make any sense to you, that's fine, because I haven't really said enough to make that point make any sense. Okay. Okay, so, all right, so that's that. Now I want to say something about negation and complements, because this is where I've been sneaking up on you. Okay, so what about negation? All right, question mark. So the usual thing is, let me define not A to be A implies false. Okay? So I will say, and you can check that not A so defined is the largest, or the universal thing, the largest C inconsistent with A. Figure out what I mean by that and check it. Okay? It's the biggest thing from this order theoretic point of view which contradicts A. Okay? That's the definition of what negation is. So you can deduce from this, let me write, so I'll write what I mean by that. So what it means is, in particular, it's inconsistent with A. If you have it together with A, the not A, then you get false. And it's the largest such thing. So that's just transcribing the exponential, right? So if A and C is inconsistent, if C is inconsistent with A, then C is smaller than or entails the negation. It's stronger than the negation. It gives us the negation, and therefore it's inconsistent with A. So that's what I mean by that. Okay, so you could say that negation is given by this universal condition. I didn't need to make this definition. I could have said, I'm going to have a not A, and not A is going to be given by rules, which give us that it's the largest thing inconsistent with A, but I didn't need to do that because by defining it to be the exponential, I get that property. Okay, so that's what I'm saying. Yep.
For A not A, can you write A not A equals false?
What?
Instead of less than or equal false, can you write equals false?
Here, less than, you mean here?
No, above. Yeah.
Well, yes, you could actually write equivalent here because this is the least element. So it's less than everything. And so therefore it's equivalent to it. But so the content in some sense is that. Is that. Okay, yeah. Yeah, that's true. Yeah, that's true. Okay, so that's what I'll define as my notion of negation. But then I will define another thing, which is the idea of the complement, which I'll write a bar here. There's never a good note. Every notation you choose conflicts with some convention, but let's call it a bar, which is the complement, which has the property that A is well equivalent to top, but it's always less than. So what I really mean, the content of this is that top is below A or not A. That's the content of it. Okay, so this is sort of like dualizing it in a certain way. Okay, so what I'm saying is the complement fills up the space. Okay, so a complemented distributive lattice is a Boolean algebra. That's what I was going to say before. A complemented distributive lattice is a Boolean algebra, and such things have exponentials. Okay, so that's the when I wanted to say something earlier. So we'll define a Boolean algebra is, by definition, the usual definition is it's a complemented distributive lattice and therefore has exponentials. What is the exponential? What is b to the a? What's the definition of b to the a? You're going to have to check this. It has exponentials. What should the exponential be? Yeah, what did you say? Yeah, except that it shouldn't be not, it should be complement. Yeah. So it's the complement of a or b. Check. So you should check this. Check that this actually is a notion of exponential. So with the Heyting algebra, for reasons which I'll explain shortly, it's better, right, to say, so another way to say what a Boolean algebra is we can say a Boolean algebra is a Heyting algebra with complements, that you have a notion of a complement, or in which the negation is a complement. Okay, that's a way of saying it. So what I'm hinting at is there's something different between complement and negation. Okay, so this is the thing I want to talk about next. Okay, so let's see, how am I doing for time? 5 minutes. Okay.
You mean to say the complement was the smallest such thing?
Say again?
You mean to say that the complement was the smallest such thing?
Maybe.
Speculation.
If I dual everything, it should be the smallest thing which fills up the space. So let's check. Needs to be smallest? Probably. I better check that. Okay, because you want a universal definition of complement. Okay, so I don't have a universal definition up here. So it's the smallest thing which fills the space. Okay, that is, if anything else fills the space, that thing is smaller than A. That's probably what I need. So the idea would be if top is less than or equal to A or C, let's call it C, then this is the smallest thing, so we'll have that this is less than or equal to C. That would be the smallest. Okay, yeah. So you want it to be as little as possible. Yeah, it's got to be, because otherwise you could just take top here or something. Yeah. Okay. Yeah. Thanks. Yeah. That's what I should have said. So this is an example of where the note takers have to make me look good. Okay. So I never made that mistake. You just like write down the truth. All right. Okay. So that's the okay. So that's the definition of complement. So what I want to point out, so that's the difference between a Boolean algebra and a Heyting algebra, and you can guess that I'm drawing the distinction because there is a distinction, because it really matters. And so the thing I want to do is I want to look at this proof theoretically, is to talk about, so the the real issue is, so the central issue is the role of negation as compared to complement. Okay? The issue is, what is the status of this guy? Is this thing equivalent to truth or not? So in a Boolean algebra, it is. Okay? And you were taught, presumably, somewhere along the way, to think about the subject, that logic is more or less the subject of Boolean algebra. Oh yeah, so I want to mention something before I get, there's something else I forgot to mention, which is a completeness theorem, which is implicit in what I said before, and this is something that you should write down and think about. I'm not going to spend the time to write it here. So since I'm running out of time, let me just mention with this. So let me finish with this, the completeness theorem. What I really described for you is the following fact. If a relationship A is less than or equal to B is true in every Heiting algebra, then it must be possible in the logic that I wrote down that B is deducible from A. That's called the completeness theorem. If something is valid in all models, it's true in all models, that is, it's true in every Heiting algebra, then it must be provable, according to the rules that I wrote down in the beginning of the lecture. That's implicit in what I had. Okay? How do you do that? Well, if you know that something is true in every Heiting algebra, and I want to show that it's provable, what's the strategy? Well, the strategy is you build something called the Lindenbaum algebra. And I really showed you how to do this, but what I want, like from the point of view of the note takers, is to figure this out. Okay, the propositional Lindenbaum algebra. And this is used to show completeness, which says that if A less than or equal to B holds in every Heiting algebra, then A true entails B true is a particular fact. Okay, I'm a little cheating here because I'm assuming that the elements of the Heiting algebra are the propositions. You can finesse that by talking about the interpretation of the proposition into the Heiting algebra by replacing conjunction by the meet and disjunction by the join, etc., in the way that you ought to do. So this notation is a little informal, but this is the gist of it, and that's called the completeness theorem. And the proof of the completeness theorem consists of constructing a particular Heiting algebra called the Lindenbaum algebra. And actually everything I've said so far is, I've already told you what it is. You just have to put the pieces together. Okay? So all the pieces you need, I'm pretty sure I said, and then you can get a completeness theorem. And it's very easy to show the converse of this, that if something is provable, then it holds in every Heiting algebra. Again, you really have to interpret the proposition into the Heiting algebra by taking conjunction to be meet, etc. But anyway, let's just fudge that. It's going to hold in every Heiting algebra. That's the soundness theorem. But the completeness theorem says the logic I showed you is complete for Heiting algebras. Okay? So it's not going to be complete for Boolean algebras. And this is what because in particular, this is true in every Boolean algebra. It's the most boring thing in the world. It's a tautology. But it's not going to be provable in our logic. And I'm going to explain why and why that's important and why that's a good thing. Okay? And in fact, I want to tell you, the whole subject of hot depends on this fact, that this is not true in every, well, here so far with Heiting algebra, but more generally in hot, that you don't have a global principle of what is called decidability. So this is called the decidability of A. This is called this is pronounced as A is decidable. A is a decidable proposition. You can decide either it has a proof or a refutation. Obviously, I can't do that, okay? If my meaning of truth is that I have a proof, and a meaning of falsehood is that I have a refutation, then pick your favorite open problem, P equals NP. You neither have a proof nor a refutation, I dare say, and so you have no grounds for saying that the disjunction holds. So such a one for which it is you could say it's decidable or decided, but it's a decidable proposition, and they will not all be decidable. And hot, although it is about a well-established branch of what anyone would call classical mathematics, so to say, to do it right relies on denying the principle of excluded middle, surprisingly enough. You get better math by denying it. So that's why I wanted to set that up. So next time I'll talk about the denial of the global principle of excluded middle, and then we'll talk about Hilbert's mistake, okay, in the debates with Brouwer, and we'll discuss that next time. Okay, thanks for your attention.